Welcome, everyone, to a very special event that's hosted by the Stanford Center for Legal Informatics, or Codex. The event today is called The Convergence of Minds, Navigating Computational and LLM Frontiers. We're so thrilled to welcome a very special guest today, one that really needs no introduction, and certainly any introduction wouldn't do justice to the incredible accomplishments he's achieved. Today, we have Dr. Stephen Wolfram, the founder and CEO of Wolfram Research. He is the creator of Mathematica, Wolfram Alpha, and the Wolfram language. He is a prolific writer, most famously authoring A New Kind of Science. Most recently, he wrote, What is ChatGPT doing and why does it work? He'll be speaking with us today about this brave new world of large language models and how to bridge them with symbolic approaches. So without further ado, please welcome Dr. Stephen Wolfram.
All right, well, let's see. There's much that I could talk about, and I'm not quite sure what you guys will be most interested in. So that prompt was about large language models and their interaction with symbolic kinds of things. So I should say the I don't have anything to. Okay. Well, I'm not quite sure where to start because we could talk about many things. Maybe I'll tell you about some of the different things I've been interested in and doing. I've been interested in kind of what computation makes possible, and this kind of started in a way. I used to study physics, and I've studied physics again more recently, but that one of the sort of questions is sort of how does the natural world work, and how do we model things in the natural world? And there's been kind of a 300-year tradition of saying we want to model things in the natural world. The best way to do that is to use things like mathematical equations. And so back in this is now early 1980s, I got interested in, for example, how do you explain sort of complex things that you see in the natural world? How do you make equations for these kinds of things? That turned out not to work very well, so it's kind of like, how do you generalize this idea of formalizing the world in terms of math? How can you generalize that to something else? And so I started thinking about kind of formalizing the world in terms of computation, in terms of programs, instead of in terms of equations, formulas, math, and so on. So one of the early questions was, okay, so if you just take sort of simple programs, what do they typically do? And so a particular class of programs that I was a big enthusiast of, still am a very big enthusiast of, are things called cellular automata. And this is a typical rule for a cellular automaton. It has a line of cells. Each one is either black or white. And this rule just says, based on a cell and its neighbors and their colors, what will the cell on the next step be like? And so if we take a rule like that, we can say, find, let's go and just say, okay, let's run this and see what it does. We have this very simple rule. It does something very simple, which you might say, that's not surprising. It's a simple rule. Obviously, it's going to do something simple. Change the rule here. We could say, let's say this rule here. Change it. It'll do something that, again, is quite simple. Okay, so then the question is, if you just use a simple rule like this, will you always get simple behavior? And let's try a different rule here. Let's try this rule here. This one, you end up getting slightly more complicated behavior. We can run it a bit longer, and we'll get some nested fractal type pattern. Then the question would be, okay, we can now think of this as sort of this computational universe of possible programs. So the next question is, if we look out into the computational universe of possible programs, what is out there? Will we always find that when the programs are simple, the behavior will be corresponding to simple or not? So we can just do an experiment, which these days is very easy to do. But when I first did this, it was a little bit more difficult. Arguably, if I've spent all these years building these tools, if I hadn't made the experiments that I myself was interested in doing easy, that would be embarrassing. Let's see. So let's just look at a whole bunch of possible rules and see what they do. And so many of them, rule is simple, behavior is, and the behavior is somehow correspondingly simple. But if we keep going down here, we get to my all-time favorite science discovery, which is this rule here. Look at that rule. It is rule number 30. That's what it is. It looks very innocuous. If we actually run it, we'll find it generates this kind of complicated pattern. Let's make a bigger version of this. Let's say run it for 400 steps or something. This is what it does. And this, for me, remains kind of the very surprising thing. Very simple rule, complicated behavior, some regularity over on the left. But if you look like at the center column of cells here, they look for all practical purposes completely random. It's an intuitionally surprising thing. You can put in a simple rule, get out something complicated. I think it's kind of the main secret that nature uses to get complicated things happening in nature is this phenomenon that in the computational universe, even very simple rules can produce very complicated behavior. So there are this phenomenon that you get sort of complicated behavior from simple rules, lots of consequences for modeling things, but we can also just look at there's some slightly more general principles that emerge from this. So one thing that, well, let's see, we could ask, let's look at this case here. Let's say we go 1,000 steps here. So this is a particular rule, and it happens to grow only on the left. And we see it's running, it's doing all kinds of things. And the question is, what's it going to do? Is it going to eventually resolve into something simple, or is it going to keep flapping around forever? Is it going to go into some, is it going to generate more and more structure? Is it going to eventually die out? The question is, how do we tell that? And it's sort of an interesting thing that it is just computing what it does. If we want to figure out what it's going to do, we are ourselves doing a computation. And the question is, how does the computation that we're doing compare to the computation that it's doing? Can we outrun it, figure out what it's going to do with essentially a shorter computation than the one it has to run itself? Okay, so the thing that sort of a big principle that I kind of deduced from looking empirically at this kind of computational universe is this thing I call the principle of computational equivalence, which says that that most of these systems are, as soon as they're not obviously simple in their behavior, they are equivalent in the sophistication of computations they can do. So that means that, among other things, that means if you ask, can I make a sort of cheaper computation that will get to the same result, the answer is no. There's this computational irreducibility to what's happening. The only way to know what the answer is to just follow the steps and see what happens. But by the way, I mean, this kind of idea of principle of computational equivalence is kind of a sharper version of things like the existence of universal computation. So the idea that you can make from one fixed set of rules, you can set things up so that you can do any computation. I mean, that's kind of the idea that makes software possible. It's kind of the core idea that made sort of modern computation possible, discovered in the 1920s, actually. Well, first discovered in 1920, but not understood in 1920, understood better around 1936, that it's possible to make sort of a universal machine. By the way, this particular cellular automaton is known to be a universal computer. And you can kind of see, you can get some idea of sort of some plausibility of that by looking at, let's see if we go like this, and do it like that. So this is what happens if you just started off from kind of a random initial condition. you see it, anti-alias like that. Let's see, maybe I can make it do it. Maybe we can make it more beautiful. There we go. You can kind of see these structures that it produces, and you might guess, oh, we could make logic, a logic circuit out of all these things bouncing back and forth, and indeed, eventually one can, and one can show that this thing, with appropriate initial conditions, is capable of computing anything that a computer can compute. But so there are all kinds of consequences of this idea of computational irreducibility. So one of the sort of bigger, more sort of issues of principle is, okay, we have gotten used to the idea that science lets us predict things, and lets us kind of jump ahead and say we know what's going to happen. Well, computational irreducibility is kind of the aversion of kind of science eating itself from the inside and saying that, no, there are things where we can't predict what's going to happen. The only way to figure out what's going to happen is to actually observe the system and see what it does. And I think that, so that has lots of consequences. I mean, it has lots of consequences in terms of realizing that people sort of say, well, science will eventually solve everything. By solve everything, they mean sort of be able to predict everything. And this kind of saying, no, that can't work. It's also relevant if you're interested in things like making up a constitution for AIs or something. And you say, we're going to define, this set of rules by which AIs should operate. And we're going to set up these rules so that nothing could ever go wrong. What computational irreducibility implies is that you will never be able to get kind of a finite set of rules that will there will always be surprises. There will always be unexpected things that will happen that you can only figure out what's going to happen by actually running it and seeing what happens. Well, anyway, so one sort of piece of intuition that I consider important is this one about the fact that you can have very simple rules in the computational universe that do very complicated things, and you can sort of understand this general principle of computational equivalence and so on. So one direction that maybe I'll mention, we'll talk about other things as well. One direction I might mention, which is a sort of recent thing, is the question of okay, what in all these possible computational rules, what about, for example, our whole universe? Does it follow computational rules? And the thing that was sort of a big surprise about 3 years ago was discovering that, yes, actually, let me see if I can pull up the relevant thing here. I need network to do that. Yes, there we go. Where is it? Here it is. So maybe if people are interested, I'm happy to talk in great detail about this. But the basic point is sort of to understand what's underneath physics, what's underneath kind of space as we usually perceive it, and the thing that has become clear is that there is a way of understanding how the laws of physics get built up that starts with sort of purely computational elements and starts with things like sort of a giant graph that represents kind of the structure of space, where there isn't anything like space as we know it that intrinsically exists. That's something that just emerges. But I suppose so there's a lot to say about kind of how physics works on this sort of computational basis. But I guess another thing that I think is sort of a big thing as far as I'm concerned is that, okay, there's all these possible things that can happen in the computational universe. There's all these things that can happen in nature, et cetera, et cetera, et cetera. There's all these possibilities in the computational universe. How do we humans kind of connect to that? And the thing I've spent the last, 40 years or so working on is how do we kind of make a bridge between the things that we humans think about and what is possible in the computational universe? And that's sort of turned into the big effort to make a computational language for kind of representing things in the world that we humans care about. And so that's our whole effort of building Wolfram language, and sort of the big idea is, how do we take kind of what the kinds of things that we're interested in and formalize them. So I view there as having been several kind of versions of formalization that have happened in kind of history, from the idea of human language, where we get sort of words for categories of things, to things like logic, where we have ways of describing kinds of arguments, to things like mathematics, where we have sort of another way of formalizing the world, to this idea of sort of computation as a way of formalizing the world. And I have to say, I think that, you know, in terms of what people do, sort of computation is a paradigm for thinking about things, and people, you know, people study for any field X, there's going to be there either is now or is going to be kind of a computational X that is a version of that field whose formalization is computational. And, you know, my efforts in sort of building our computational language, I guess I see as being analogous to what people did, I don't know, 500 years ago or something now, with mathematical notation. People found a streamlined way to represent mathematical ideas, kind of a language for mathematics, and that enabled, you know, algebra and calculus and basically mathematical science. And so I view our effort as being to try and do the same kind of thing, to make sort of a notation for computation that will allow one to make kind of computational X for all X. And so there's lots to say about kind of what's involved in making such a language, but I see it, as I say, as being this way of taking these sort of infinite set of possibilities in the computational universe and sort of crispening them up to the point where we can use them conveniently as humans. I mean, it's sort of a different mission from the programming language mission. Programming language mission being more, we've got computers, they have certain intrinsic operations. How can we tell computers what to do in terms of the intrinsic operations they know how to do? The sort of computational language idea, which, you know, can also achieve the kinds of things programming languages can achieve, but it's sort of a more ambitious effort to try and take things in the terms that we think about them and formalize them so that we can get our computer to kind of help us with those things. Now, you know, how do things like LLMs fit into this? I think we got to demo something here. Let's see, what can I find here? Let's try this. Just for fun, we can try something. See, I'm used to demoing pure Wolfram language stuff, where I know things are going to work. But if we now we're talking to an LLM, and I have no idea what's going to happen. So what can we ask it to do? Let's say draw a circle that is half blue and half red. Okay. Now, you see what's sort of interesting here? That's a bad sign that there's things that showed up red there. It's a bad sign. Okay, let's try running it and see what happens. Well, it's not bad. Okay, that worked. So what's interesting here is, you know, we said something kind of vague here. It produced some piece of precise Wolfram language code, which is not the most elegant code I can imagine, but you know, you can kind of read it and see what it's doing. Maybe we can try, let's see what happens if I say, do the same for a dodecahedron. I think I give the chances of this working. That's a bad way to do it. That's not the way I would do it. But let's see what, you know, we can kind of see there's a small enough piece of code here. We can kind of see what it's doing. And it's saying, well, let's see what happens here. Bad. Okay.
I think that it's saying it needs more data to actually, because it needs you to tell it what all of the faces.
Oh, well, okay. Let's just see what happens if I say this. Not half the faces. Okay, well, fine. All right. Okay, that's actually pretty smart. Let's see what this is going to do. All right, let's try this. Again, it failed. All right, now we have to look. This is not how I would do this at all. It's saying if the number of the face is even, then make it red, otherwise make it blue. Actually, now I'm confused by why this isn't working. Well, let's just see. Let's take that piece. Again, it wouldn't be how I would do it, but whatever. Let's take that piece and let's... one of the nice things about a symbolic language is that any piece of code can just be run and does something. So there, that produced... okay, so I think I know why this didn't work. Okay, that looks better. So that's now hopefully a bunch of... what it didn't know is that the way... Okay, so now let's try running... Let's try taking this. Let's try saying faces equals this. And then let's try running this. That's very weird. That's not good at all. I think we're better bet here is to take, I don't know what this is. This is kind of competitive programming with an LLM. It's so competing with the LLM. I think if we say, let's try just something like this. Let's try riffle into line 44, and let's try random choice of red and blue. Let's see what happens if we do that. Oh, that wasn't very good. Let's try saying, let's try doing this. Let's try saying make random choice red and blue. Let's do that. Well, whatever the length of that of line 44 was. Okay, so there's a bunch of random reds and blues. Now let's say transpose this and the thing on line 44. And now let's say, well, here, let's just see what happens if we just say, show that as a piece of 3D graphics. Okay, wasn't bad. So it took a little bit of human effort to get, to untangle this. But, I think one question when we look at, one thing we can kind of ask is, when the LLM is doing its thing and producing, let's say, code or human language or something like that, how should we think about what it is doing? And I guess that let's talk about the human language case, although it sort of applies to code as well. There's a question of what, why is it possible to do what an LLM seems to do, of being able to generate sort of fluent human language? It's something that was surprising to, I think, everybody, that there was this threshold passed where LLMs started to be able to do that. And I guess the thing is, what was it that LLMs figured out, so to speak, that let them do it? And I think the answer, although the science of this is still not well developed, I think the answer is that LLMs noticed certain regularities in language that we humans hadn't really noticed. So regularities we had noticed was things like syntactic grammar, the fact that language is formed, in English it's noun, verb, noun is a typical kind of structure. But knowing that language is formed as noun, verb, noun doesn't guarantee that the sentence we will get out will be meaningful. It could be something that is just syntactically correct but completely meaningless. But my guess is that there's, you can say, well, what additional rules are there beyond saying it's noun, verb, noun? What additional rules are there that give you just sentences that are plausibly meaningful? And so one class of additional rules are the ones that exist in logic, and one can kind of think of, how does one deduce logic? Well, you look at a large number of sentences, and you see that there are sentences which have the pattern of, if A is a B, then et cetera, et cetera, some kind of syllogism. And you see that there's this pattern of lots of sentences working that way. And then from that, you can kind of lift what we might describe formally as sort of logic, but you can kind of see that there's this linguistic pattern that you can then apply. And when you're being an LLM and you're just trying to complete sentences and so on, you're sort of able to apply that pattern. And so I think what we're realizing is that there's kind of a higher level set of patterns about a sort of semantic grammar of language that the LLMs have kind of discovered. And I think, actually, I've long been interested in whether there's sort of a symbolic way to represent general discourse in human language. And I think the LLMs have just sort of convinced me that, yes, there really is a way to do this. And actually, we've been doing a bunch of work on trying to create that kind of symbolic discourse language, as I'm calling it, using LLMs to help that construction. And looks very promising that there is a way to kind of represent kind of lots of what we talk about in human language in a kind of symbolic way. And that kind of tells one, among other things, that a lot of what LLMs are doing are sort of taking a very long way around using neural nets to do these things. Is kind of a long way around relative to what's sort of symbolically possible. I realize I'm not sure what you guys are interested in, so I've been sort of talking about a few things that I've been interested in, and maybe the best thing for us to do is to try and turn this into some kind of discussion about whatever you guys want to ask about. I've just sort of told you a few different things that I've been concerned with. Maybe we can turn this over. Who has a question? Yes, please.
So I'm a mathematician, also at the law school. I'm curious about, first of all, your cellular automata, like the parameters you're adjusting. Is that the cellular homology's dimension, or what are the specifics? I think there are like a total of four numbers that you're adjusting. Could you tell us a little bit about the demo, as in what exactly your rule is for us to understand?
Yeah. So I mean, let's take this one, for example. All this is doing is saying you've got these cells. So, for example, right at the top here, let's make a smaller version just so it's easier to see. Okay, so let's take this cell here. Okay, how do we figure out what color that cell is? Well, we look right above it, and we see that it's black, white, white. So we look in this rule table here, and we see black, white, white makes black. That's all that's going on, nothing more. It's very trivial. So the big surprise is that even though that's that trivial, what comes out is not trivial. And that's the thing which, in terms of intuition, surprised me a lot and was something people had seen examples, quite a few examples, of places where there were simple rules that produced complicated behavior, but the idea that that was a general phenomenon is something that we didn't figure out until, I guess I figured this out in the early 80s. And there are examples, like the digits of pi are another kind of example, more complicated in terms of the rules, but there's a specification of how you get the digits of pi, and that is, it's a definite specification, but once you've generated the digits, they seem random. This is that kind of phenomenon. Please, yeah.
How do you think large language models will impact and should impact academic research?
How do I think which?
Large language model, how will it impact and should it impact academic research?
Well, okay, so that one question is, there's research and there's academic research. For example, well, gosh, let me think where to start on that. Given that you discovered something, how do you present it to the world? There is this standardized way of doing that, which is an academic paper. And, one of the features of large language models is the thing they're pretty good at is you give them sort of a compressed set of facts, for example, and you say, make a report based on these facts. And they can sort of puff it out to a big report based on those facts. That is a useful transport layer. I mean, it's like you're filing some report about something. You have 5 things you know. You turn it into this big report. then whoever's reading the report cares about only two things from your report. So they go, it puffs out into this big report, and then another LLM is reading that report and says, the conclusions I care about are these two things. So the cynic might say, the future of academic research is people taking some specific research finding, sort of puffing it out into this thing that's called an academic paper. Then the reviewer of the academic paper feeds it to another LLM, which concludes, everyone's very cynical about these things. The peer reviewer is asking the natural selection question, does the publication of this paper increase my fitness or not? And then do what they do from that. But I think, a little bit more constructively, I think the thing that I see as being sort of the big sort of trend of the century in academic research is the computationalization of everything. And the formation of computational X for all fields X. And I think can large language models help with that? Somewhat. They provide a better on-ramp, like, as I was sort of typing, stuff a few minutes ago, it's kind of like there are people who fluently know computational language. And like, for me, I can start typing, computational language code before I could tell you what I'm going to type, which is sort of the definition of being fluent in some language. You don't have to think about things in one language and then translate to another. You just fluently start typing things. But it is a useful on-ramp for people who know natural language to be able to use that as a way to get sort of a leg up on making a precise computational language. I mean, we've been very successful at that with Wolfram Alpha, where one goes, Wolfram Alpha works by going from natural language, Wolfram Alpha has no documentation. There's there's nothing that tells people how to use it. It's intended to just work by people typing in whatever they think of typing in. And then it translates that into its sort of precise internal symbolic language, which is just Wolfram language, and then computes from that. And I think the ability for people to take sort of the things they are just sort of thinking about and can describe in natural language and get some way to convert that to something more formal of computational language, that's something that I think will broaden the computationalization, speed up and broaden what can be computationalized, so to speak. However, I think there is a thing that blocks this, which is I think the problem is people don't have an idea about how to think computationally about things. There's a bunch of sort of concepts about, I don't know, if I were to look at, let's take this room, which has a bunch of lights, right? And so the question is this room going to be uniformly lit? How would we think about that question? I don't even know what do we mean by uniformly lit? How would we start, sort of thinking about that in formal computational terms? I think that the thing that is somewhat lacking and is not typically taught, it's not part of computer science, for example, to teach people how to think about the world computationally. And actually, one of my upcoming projects is to try and sort of write this big treatise on kind of computational thinking and the question of how you explain to people, how you make sort of a computational description of the world. I kind of think it's kind of interesting because there's lots of sort of facts about how different aspects of the world are computationalizable that it's worth knowing if you want to figure out how the next thing you want to computationalize can be done. And I also think it's this general kind of thinking about how to formalize the world is something that is, it has sort of more similarity in some ways to philosophy than it does to many of the kind of STEM subjects that people teach, which are much more taught in terms of the mechanism of given that you know what problem you're solving, how do you solve it, rather than sort of how do you define what problem you're trying to solve. So I don't know, there are a few thoughts, but I think, the thing that I think is one hopes is the future of lots of sort of academic research and so on is representing things in a more formal way using computation, because that's what allows you to progressively build these different fields. Because that, if it's just a bunch of words, then everybody has to read that paper again, and try and construct something concrete. I mean, I don't know, and the things that I write, for example, one of the things I've been keen on doing is, you know, if you go and, I don't know, find, where it is, if you know, any random thing I've written, you can, you know, kind of click one of these pictures, and in theory, you can just go and when you click it, you paste it, and you get some code here, and hopefully, you know, this is again living dangerously. You click that, and it grinds away for. I don't know. Maybe this picture. Okay, there we go. And it actually makes the picture that was, you know, in the thing I wrote. And in fact, as just a practical matter, this is really powerful because people can then, you know, take what one's done and immediately build on it. It is kind of surprising that this kind of reproducibility, computational reproducibility, is not, you know, has not become more common over the 40 years that I've been talking about this. And, you know, part of the reason is because it's actually kind of hard to make sure that the code you write actually runs and package it up properly and so on. And I think people, you know, it's easier to just write a bunch of words and, you know, make it roughly right. Now, whether, for example, you know, perhaps the LLMs can help one a bit in going from the bunch of words one writes to some first attempt, as we saw earlier, at some sort of computational language version of things. So a few thoughts, at least. I mean, there are other, I don't know, I mean, there are things one could hope to do, like take literature in some field and sort of make it computational, you know, take, you know, extract structured data from unstructured text. Okay, so we've been in the business of doing that for 25 years or something, curating data about everything in the world. And so we've obviously used LLMs to try and assist with that. And my basic conclusion is that it makes it about, it increases the speed of doing that by about a factor of 2. That's the current observation. So it's not a slam dunk. You just feed in an LLM, you give it some unstructured stuff, and amazingly, it you know, it untangles everything. No, that doesn't work. It makes too many, you know, there are too many things it gets wrong, and too many things where you don't know if it's right or wrong. But I think the kind of thing that we saw earlier here, of it gives you a hypothesis for what might be the correct, precise thing, that's useful. And you know, in like enterprise software settings, you can say, there's this company and it's got all these databases, and here's the internal documentation of these databases. Now hook these things up so that we can query them in a sensible way. You know, if it succeeds in coming up with a way to do that and it's correct, then it's all good. And you know, maybe it'll be wrong 10% of the time and you throw away those cases. But you have to have sort of a workflow where you can make use of the fact that even though it isn't right all the time, you know, you can get something out of it. So, but I think, you know, this structured data from unstructured, you know, like academic literature, I think it assists, but it does not, like, you can't, you know, solve that problem completely. I mean, there are other things like, you know, sort of hypothesis generation of various kinds about, you know, one of the things that I'm kind of thinking LLMs will be able to do, although I don't think they're quite there yet, is sort of grand analogy making. So, for example, a bunch of things that I don't know, somebody like me sort of prides themselves on being able to figure out. It's things like, there is an analogy between metamathematics and general relativity. Okay, and you can conclude a lot of things from that. Now, is it plausible that an LLM could come up with that conclusion as well? I think probably yes, because it can see that the pattern of things that are said about general relativity, the pattern of things that are said about metamathematics have some correspondence, so it can make that sort of, potentially make that jump. It isn't quite possible yet, but I think that is something that I expect will happen. And what I think it is, you know, I don't know what the actual sort of user interface to such an effort would be, but that's, you know, I mean, it's kind of like, I've got this question. What out there in the world of science is analogous to this question? Actually, I guess I've tried some you know, prompts like that with rather banal results. But eventually, I think that kind of thing is a potential, you know, pretty powerful direction. Yes?
You mentioned how simple rules can often produce You mentioned how simple rules can produce rather complex behavior, and that sometimes it's impossible to predict what's going to happen unless you're going to actually run the simulation to see. And so I'm wondering, it's sort of similar to solving a differential equation where you have a pretty simple rule that, solution to the differential equation would be the behavior of the system. And very often we can get a shortcut. Instead of simulating every step of differential equation, we can just guess the solution, for example, plug it into the differential equation and show that it works. I was wondering, how do you know that there is no shortcuts to these complex systems that we just were not yet been able to figure out?
Okay, so several points. First of all, in the case where you have it's like the NP problem case, where you have a thing where once you have guessed an answer, you can check whether the answer is correct. And that's sometimes true. I mean, in the world of differential equations, or in the world of it depends on your differential equation, whether you can say, oh, we've got this candidate solution, can we check that it works, versus, we have to evolve the thing. This question of how can you show that there's computational irreducibility, it's essentially a diagonal argument. I mean, you're basically saying that if you have a system where the inner behavior of the system is capable of corresponding to any possible computation, then there's no way that you can have something which in general will go faster than it, because it can do anything. And so nothing can, that's the basic structure of the argument. And we know of particular examples. I mean, in the case of cellular automata, the simplest one we know is that Rule 110 cellular automaton. There's one, if I can find it here. This is in Turing machines. I had this guess a few years ago that Turing machine would be, which is the first Turing machine. If you enumerate possible Turing machines, it's the first one whose behavior is not obviously simple. And interestingly enough, turns out to be universal, which is kind of a big piece of evidence for this principle of computational equivalence that says as soon as it doesn't look obviously simple in its behavior, it will be equivalent in its computational sophistication to everything else. And so, for example, computation universal. So that's an example. It's another case where we can kind of see, yes, this is a case where, because it's universal, et cetera, et cetera, et cetera. So with respect to differential equations, I mean, the problem with differential equations is they're not, they involve the continuum. And the continuum is not it's not easy to map that into something where we can talk about computation and so on. I mean, in differential equations, there certainly are examples. So you can do the same thing in differential equations that you can do in cellular automata, for example, and you can just go, somehow this is the methodology of my life or something, you can just go and look at these systems and you can just enumerate possible differential equations. So these are some popular differential equations, like that's the wave equation. You started off with a little Gaussian wave packet there, and it'll make two waves here. But then you just go and start just enumerating equations, see what they do, and you don't have to go very far. These are very simple nonlinear wave equations where you start with some initial sort of Gaussian thing, and you get these complicated pieces of behavior. One of the things that is sort of challenging is to know whether these answers are right. I mean, we've used these since the early 90s, actually, as tests for the numerical differential equation capabilities of mathematical and Wolfram language. But can we know that these are right? Well, we can run a bunch of different numerical simulations, and we can say these simulations agree. They don't seem to depend on sort of cutoffs and so on. But there isn't an analytical, we know the answer here that we can compare with. But that's, this is a case where you see phenomenon pretty similar to the Rule 30 cellular automaton, except that nobody would ever have concluded that phenomenon from looking at these, because they would always be worried that the reason we're seeing all this funny behavior is because of some numerical round-off issue. So it kind of takes looking at this discrete thing to be able to do that. Now, when you look at these continuous systems, one of the things that's confusing is there's often a symbolic representation of the system. So for example, let's talk about the number pi. We can say, it has an infinite number of digits, but yet we can represent it symbolically just as that symbol pi, and we can make certain deductions about it. And so there's the question of how far can we go by symbolically representing real numbers, for example, and just manipulating them in symbolic form. And the answer is you can go a certain distance, but there are always things which sort of go beyond what is purely computational if you want to kind of know everything about things with real numbers. So it's a sort of a separate branch, and actually it's kind of an interesting thing that, gosh, there's a bunch of kind of, oh, maybe I'm getting too far into philosophy of math and so on, but there's a bunch of things about kind of the continuum hypothesis and these questions about the distinction between sort of the integers and real numbers and how that works computationally. But long story, people are interested. Yes, please.
So you talk about these grand analogies, like for example, between the computational model and general relativity.
Yep.
But don't you, this is a question, is the fact that it's always, large language models will always be large but discrete? Do you think that's a problem for those kind of analogies?
Do I think that the fact that, well, I mean, one feature of neural nets, which is kind of weird, is that neural nets are real number computation, basically. They are, it's funny, in the history of computation, right? Turing machines were a 1936 story, and neural nets were a 1943 story. And already at that time, neural nets involved real numbers. And the operation of neural nets and their training involves basically calculus-like operations where you're making incremental changes. I don't think it needs to, but that is how it's done right now. I mean, my guess is that there's a way of, if we understood more about kind of the geometry of discrete computational systems, we would find ways to be able to do incremental training basically directly in this kind of discrete digital space without going through the sort of real number continuous case. But I guess are you asking whether, so large language models formally involve real numbers. They don't in practice, and it doesn't seem to matter. We can grind down the precision in a large language model a long way, and it doesn't seem to do anything qualitatively different. So I think, but I don't know. I mean, in terms of I'm not quite sure what you're asking. Try again.
Okay, I'm asking, in order for the large language model to really understand general relativity, do you think it needs to understand the continuum? And does it understand the continuum right now?
Okay, so I don't think general relativity. I'm pretty sure, and this relates to our whole story of our physics project. General relativity is the emergent phenomenon that comes from lots of discrete things happening underneath. It's just like, in fluid dynamics, we have continuum fluid dynamics, and we can talk about the Navier-Stokes equations for fluid dynamics and so on. But in the end, we think it's a bunch of discrete molecules underneath that are making the stuff, producing this stuff. And so similarly, in general relativity, we're pretty sure, actually, we're really very sure at this point, that discrete underlying structure to space is sufficient to give you emergent general relativity in the same way that discrete molecular dynamics gives you emergent fluid dynamics. And in fact, it's kind of fun that the recent thing has been that a bunch of our models have turned into some practical code for doing general relativity simulations, which people are starting to use, not really caring what the underlying model is. They just care that it reproduces, it's a good, quotes, numerical scheme for reproducing general relativity. So I think that so first statement is general relativity is an emergent thing that I think comes from something discrete, and I think we might even get, I don't know how many years it'll be before there's experimental evidence that that's what's actually going on. It depends on this one parameter in our model, which is basically the size of the elementary length, which we don't know. Just as people didn't know how big molecules were, and they kind of lucked out that Brownian motion was an observable phenomenon, given the size of molecules and the resolution of microscopes and so on. We may or may not luck out in this century, so to speak, in terms of being able to see the elementary length in space-time. But I think in terms of a large language model and what it conceptualizes about general relativity, I don't know. I think it's just knitting together words. I don't think we should. I think that we should not. What can I say? I mean, there's an interesting question: to what extent given that it read everything that's been written about general relativity, can it make a different formal statement than we've been able to make? And I mean, the one example where this has sort of worked, even with large language models to some extent, is protein folding, where it's something that is not directly related to human language, but is something where it seems like the same sort of pattern of ways to think about things. And what seems to happen there is that the large language model effectively has found certain regularities in proteins that we humans had not noticed were there. And so if you ask the question, are there things, if we fed the large language model everything that's known about relativity, would it be able to make statements? I don't know. I mean, I think in that, that's the real question is, could it make different things? I mean, can it make extrapolations about what's going on? Can it produce statements that we humans would understand? These are different kinds of things. And is it useful for? I mean, okay. Let me give you an example. Let me just pull something up here. Where is it? So this is one of my little discoveries at some point, was that is the simplest axiom system for Boolean algebra. Okay, and the proof is, well, let's see. This is a version of the proof here. Oops. It's just so that's the proof, and it's a big, complicated thing generated by automated theorem proving. And the question is, is there a way to take this and make it something that is a useful piece of sort of human-level mathematics? So far, this has not been possible. And so, that you can ask the same kind of thing for, is there a sort of human-level statement about general relativity that could be deduced that we don't know yet? And, I think that's not impossible. I haven't seen that happen yet. I mean, the history, well, yeah. Other things, yes, please.
So the computational scheme of a neural network is allegedly, people say it's different from computers and logic and discrete sort of reasoning. So people say they're distinct. So we get this weird phenomenon where computers generate humor, but they can't add two numbers robustly, because that's how neural networks are. Is that something inherent in our brain? Are there two different mechanisms? Is this working? In our brain, how should I turn that? So should we imagine that in our brain, our ability to reason discretely is because of a different hardware, or is there a neural network that does everything in our brain and we just haven't figured out the algorithm for networks?
I kind of think that one of the things one's observing here is the power of universal computation. That is that all these different things, it's some random neural net, it's a cellular automaton, it's a digital circuit, they all basically compute the same kinds of things. Now, is a neural net efficient at doing, can you in principle, 1943, McCulloch and Pitts proved that you can make a Turing machine out of neural nets. Okay, so we know that's possible. We could now go and take a trillion, trillion weight, LLM or something, and yeah, we can make a Turing machine out of it to a high approximation. I don't think that's a particularly interesting fact.
How big is your brain, though? It's not that big in terms of efficiency. You are doing discrete reasoning, and
rather poorly, I think. Brains do that pretty poorly. People can't run code in their brains, for example. Nobody can, given a big piece of code, I don't think anybody can tell you what it's going to do in their brains. And I think that's, this is the thing that's interesting about what's happened, is that, brains do a certain set of things. We manage to build technology that goes off in a somewhat different direction and manages to do certain other things very well. The physical world manages to do certain kinds of things well. that are, again, a bit different from what brains do well. Neural nets, I think, are, it's a particular model of computation. There are certain kinds of things it does well. We have built our world to be wrapped around the things that brains do well. And so it, to us, looks, outsize important that, we've chosen those parts of the natural world for which our brains can figure out what's going to happen. We don't, for example, in fluid turbulence, we don't live in worlds where fluid turbulence is a tremendously important thing, because that's not really accessible to brains. And so I think that's, it's kind of a, we can live happy lives just doing things that brains are capable of kind of wrapping themselves around. And the universe is doing things which are different, and mathematics is doing things which are different. I mean, as this question about whether the mathematics that we choose to explore is stuff that is kind of humanized is that's I think what's happening. There is, we can think about mathematics at the level of all these little microscopic axioms, which is very non-human mathematics and not very accessible to our brains and not very interesting to us. I think that's the, I think basically we're pretty bad at doing kind of computational kinds of things in our brains. And but it doesn't seem to matter much to us because we built our lives and our world to deal only with those things that we're reasonably good at doing. That would be my, yeah.
About the concept of computational methods, do you mean like mathematical equations, something more deterministic and clear, or do you also mean deep learning neural networks?
For what? For
what? Sorry.
For you mean making different fields of science and so on computational?
Yeah. So like in general. Hello.
I can hear you. I think everybody can hear you. This is a good acoustics room.
So like in general, what's your opinion of making scientific observation or scientific advance based on deep learning, like based on black box that is not perfectly accurate or perfectly clear?
Well, I mean, yeah, right. So I mean, the question is, are the humans expected to understand it? And most of what science, natural science, tends to be about is taking what exists in the world and trying to make a correspondence between that and a human accessible narrative. Right? In other words, if science is about saying, that has been the traditional role of science is to sort of make human accessible things which happen in the natural world. Now, I think there are plenty of places where, I mean, okay, can one understand everything that happens in the natural world? No, we cannot. This is the story of computational irreducibility. We have thought that we could understand, with the kind of mathematical idea about how science is set up, we kind of have this notion that there should be a way to sort of mathematicize everything in the world, but I don't think that's not going to be possible. The things that we have chosen to concentrate on, things like physical science, are things which we have successfully mathematicized. There are plenty of things out there in the world which we have not successfully mathematicized and which, sometimes we don't even call them science. Now, in terms of, will we be able to, what's the trade-off between sort of the black box neural net versus the, here's a human understandable narrative of what's going on. I mean, in the end, most of what happens in the world is computationally reducible. So black box neural net or specific explanation, they're still not going to do you much good. They're going to be things that are surprises even beyond what the black box neural net tells you. The black box neural net is good at, because it is similar to how brains work, it's good at telling you things that are the things that we have considered relevant from brains. But I mean, in terms of what, okay, in terms of the ways to think about science, I think the more important thing is defining the questions that you're asking. How do you define the questions you're asking? Once you say, I'm going to try to decide, is this this kind of rock or that kind of rock? and that's being done by some machine learning classifier whose innards you don't understand. The first question is, what is the question you're trying to ask? Is it, is it this kind of rock or that kind of rock? What is the, how do you define the question? Once you know, I think the more important thing in making progress in science is being able to specify how you define questions. I mean, that's, in the case of mathematics, for example, there was, being able to have a mathematical notation that allows you to set up questions like, are there an infinite number of twin primes or something? That's a huge step that's taken right there in having that notation. Then the question of proving that is a different issue. So I kind of think that the most important thing in terms of sort of the definition of computational X fields is this thing about defining what the questions are in a formal way. And that's less important than whether you get to see inside the black box about how one particular thing was resolved. Yeah.
Ask a question. So my question is like, after hearing your lecture, I feel like that's really bad news for lawyers because you are suggesting that even if we have, thank you so much, even if we have very clear rules and very consistent implementation or enforcement, then the result could still be chaotic. I was wondering if at a general level, is there any way that we can identify what kind of rules will likely to produce unpredictable results, or is there any way we can cleanse out the chaotic things that would be happening?
Right. I mean, you get a very boring world if you have one where you can predict what's going to happen. I mean, in other words, it's kind of a trade-off between, and it will be, I think, sort of big societal issue for the future is, do we let AIs do we tell the AIs you are constrained, constrained in this and this and this way, so that we can predict that the AI will never do anything crazy, right? That's scenario number one. If we insist on that, then the AIs can never do anything, in a sense, truly creative. They can never break out of this sort of box that we put them in. Possibility two is we let the AIs do some things where we haven't completely boxed them in which case they will occasionally do surprising and unexpected things. I mean, it's similar to, the natural world also does, is doing all sorts of computations, and it occasionally does surprising and perhaps, undesirable things. And I think that's, that's the trade-off, and people have to decide, either we want the world to be entirely predictable, nothing could possibly go wrong in some definition of what wrong is, which is its own separate issue, versus we have, versus we have the possibility of sort of unbounded computation. I mean, it's worth realizing that in terms of us humans, for example, we like to think that we have some sort of free will about what we do and things like this. If you, if you ended up in a situation where science had been infinitely successful and everything could be predicted, it would be as if, what is achieved by the passage of time? If you can immediately say, oh, I know the answer, I know what's going to happen in the end, there's no reason to kind of live through the steps, and there's no sense in which you can think of yourself as having kind of free will. But in terms of legal systems and so on, I think this question of can you define a, I think one of the things is you will never be able to define a sort of set of rules where, for the world, for example, where nothing unexpected can happen. So because the world itself is full of computational irreducibility. So you say, I'm going to put these and these and these constraints, and it's all going to be good, and nothing, like, for example, we could decide, we're going to set up let's say the world is run by AIs, and we set up a bunch of rules for the AIs, and we set them up in 2024. We make a world decision that the AIs are going to have this set of rules. And then you say, well, will anything unexpected ever happen? And the answer will be, because even the operation of the physical world contains computational irreducibility, it's inevitable that situations will arise that were not, that sort of couldn't be anticipated from that set of rules. And so, then something weird will happen, And then you'll have to say, well, what do we humans want the AIs to do now? We have to patch the set of rules that we gave. I mean, so in other words, I don't think there's a way, I don't think there's any way, given that we exist in a physical world that has computational irreducibility, I think we will never be able to, I mean, if we could successfully kind of isolate ourselves in some box that was not subject to sort of external physics, we could potentially set up a set of rules that would kind of, always be predictable, never be, as you were saying, chaotic, so to speak, but it will be a very boring world. It will be a world in which there is no sort of free will. There's, we could always know what the outcome would be. There's no point in sort of living life because you just know what's going to happen in the end. I mean, I think this question of sort of how you, well, okay, so this sort of raises questions about, okay, we've got these AIs. I realized as we have all this systems, we have a whole bunch of tooling, which I didn't show you much of, for dealing with LLMs and Wolfram language. And so I kind of was realizing at some moment, quite a number of months ago now, I was about to set it up so that, the LLM can execute arbitrary Wolfram language code on my computer, okay? So, I just have to I just write a piece of code and then press the button, and now it can do arbitrary things on my computer. And that was a sort of moment when I realized I actually should pay attention to sort of AI governance questions, because by the time the LLM is running my computer, it can do anything. It can use these APIs, it can go and access all kinds of things. What should I get my LLM, what should I tell my LLM it can do or cannot do? And this, I've thought for a while actually about sort of the, how do you make sort of an AI constitution of what the AIs should do? And my initial theory had been, imagine 200 different provisions that could be in this constitution. Like, for example, an AI must have an owner. An AI must, all sorts of different things. And you will typically have a situation where some people will say, yes, I want, provision number 7. And other people would say, no, 7 is terrible, I want number 11, so to speak. People won't agree about what provisions there might be. But, can one even come up with reasonable sets of principles that one might hope that AIs would follow? And I was having a somewhat hard time with that. But I also, then there's the question of, okay, how does, another sort of type of topic is, in the modern world with AI and all this kind of thing, how do we imagine governance, so to speak? And so one thing I was sort of playing with was the idea of a promptocracy, where everybody just writes a prompt. And instead of, for example, voting on what you want, you just, write an essay, write about how you want the world to be. Then you feed millions of essays into a big AI. And then every question that comes up, you ask the AI, what should we do now? And so then you immediately will say, well, how does the AI, solve sort of utilitarianism and so on? How does it know, if it knows that 90% of the prompt said we should do this, but 10% said absolutely not, how does it deal with, how does it deal with that question? And you can kind of realize, you can kind of recurse a bit, because those prompts can contain information on how, people's preference for what do you do in the 90-10 case and so on. So you can kind of imagine this, and I have to say, I have not figured out, my intuition is that any such scheme will sort of grind one directly into lots of old questions of political philosophy and will not really solve them, but it's sort of an interesting thought experiment, what actually happens. And one other thought along these lines, I was thinking about, one problem with legal kinds of things about AIs is that AIs, in a sense, have no skin in the game. AIs, we imagine that an AI, you can just switch off an AI and it's okay. But so my proto theory of that, of how to think about that is imagine you have this whole society of AIs. Imagine it's lots of interacting AIs. And imagine that there's an AI that does something bad. Then the theory would be, if that AI is essentially cut out of AI society, then it no longer has an effect on the world. In other words, if what's happening is there's this whole society of AIs and they're running all kinds of things in the world, but one AI is not trusted by the other AIs, and so they effectively cut it out, then it's as if that AI, got killed. It wasn't, the AI might still be there, but it's not communicating with anything else in the world. And so I kind of was thinking, I have not figured this out, so it's sort of consider it an exercise that would be nice to solve. Is there a mechanism, if you have this kind of society of AIs, is there a mechanism whereby you can kind of set it up so that the AIs are motivated? Because in some sense, while the AIs may not have an intrinsic motivation, the fact that an AI might disappear from the society of AIs makes it, that while it doesn't feel bad about that in some sense, or we don't imagine that it does, as a practical matter, it has achieved the objective of, that AI is no longer part of the system, so to speak. So is there a way of kind of setting up the governance of this kind of society of AIs so that that is the analog of the AI having skin in the game, is that it is, if it doesn't do the right things, it is cut out of society, so to speak. So I haven't, again, I haven't untangled this, but this is kind of an exercise of something I was trying to think about. So, yes, please.
You were talking about like the cellular automata and how some like exhibit this like very complex behavior. I guess like you could understand it as like chaos, but it also makes me think like maybe this has like more informational content or like more entropy built into like some sets of rules. And then this then made me think about like using these things to like model physics in like a more abstract computational form, and how like probably like the Boolean space for like our real physics is like high entropy, and like entropy goes up given the second law of thermodynamics. So I wonder if you've like looked at other like sets of rules and looked at like the informational content there, and whether this says something about like, can we come up with like a formulation of different systems or like physics or like a possible world where like there wouldn't necessarily always be increasing entropy, or just like kind of generally, do you have like any interesting thoughts there?
Yeah, well, okay. So actually, one of the first questions I ever got interested in physics was why the second law of thermodynamics is true, which I got interested in when I was like 12 years old. And 50 years later, I think I understand the answer. I just wrote this thing actually about computational foundations of the second law. And the main point of the second law, you start off talking about things like, gas molecules bouncing around in boxes and so on. And it turns out that that question is, the way to think about it is I think I have some picture at the top here. I can't navigate my own thing. This is just, you start off with something that is very orderly, and you end up with something that looks to us random, okay? And entropy is basically defined as you know certain things about a system, how many microscopic states of the system are consistent with the things you know. So for example, you say, it's a gas, it's in this box. How many possible configurations of molecules are there that have the gas be in that particular box? You have a box of a different size, there are a different number of configurations. So entropy is the number of configurations consistent with the description that we have of the system, okay? So the thing that is surprising is that even a system which you have a very simple initial condition, for example, where we say, well, this system, we can plainly see that this system is very simple. There's, at our level of description, there's just one version of, there's just one state of the system that's consistent with what we know. But then, after it runs a while, then things at our level of description, we just say it looks random. And then there are many states of the system that are consistent with what we know. And because we're saying it looks random. I think the way to think about it is, okay, so I think this is all kind of a story of computational irreducibility, actually. And I think what's really happening in the second law is that we're taking whatever initial conditions we can set up, and we are effectively encrypting those initial conditions to the point where observers like us, who have only bounded computational capabilities, are incapable of decrypting it and finding out that it actually came from a simple initial condition. So to us, it just looks random because we can't do the decryption. If we were organisms different from the ones that we are, we might be able to do the decryption. So one thing actually happened even very early in the history of the second law of thermodynamics. People started talking about the heat death of the universe, that eventually, a trillion years in the future, the whole universe will just be a gas and thermal equilibrium. And every sort of interesting thing about the universe will be gone, okay? But in fact, by the way, if the laws of mechanics are reversible, as they seem to be, we could go back from the state of the universe a trillion years from now, and we could reconstruct what's happening in this room now, for example. And so, but it is the point is that the reason we think about this heat death thing is that for observers like us with our current capabilities, what will appear there in the future will seem random. And so we won't be able to, in our way of describing things, it will look like it's just a random high entropy thing. But actually, if we had a different way of observing what was going on, we would be able to say, oh, there's all this detail, and it came from the civilization that went extinct or whatever else. So, I mean, I think this whole story of entropy and so on is very, I think one finally can understand it in terms of these computational ideas. Just to say one last thing here, one thing that's kind of interesting is what happens is, does entropy always increase? And does the entropy for observers like us always increase in the way that the second law says? And one of the things that happens is you get these weird systems. There's an example. That's a reversible cellular automaton system that has all kinds of structure. And you could go on, you can look at what it does. These are all reversible systems. Look at this thing. It looks like it's doing something purposeful. And I think that actually in molecular biology and in living systems in general, I suspect that one of their characteristics is that they have this kind of, seemingly purposeful behavior. It's not like, you ask, what is living tissue? Is it a liquid? No, it's not really a liquid. It doesn't have molecules that bounce around randomly. It has rather orchestrated motions of molecules. I suspect it's some other kind of phase of matter that corresponds to this kind of computational thing. This is a long story, which is as yet, the end of the story is not yet known. This is just the beginning of a sort of story of how one thinks about molecular biology computationally, which is a kind of a long-running issue with the second law of thermodynamics, is how living systems relate to it. And I think I have to disappear here. So I thank you all very much. And
thank you so much again, Dr.